Cadista, prima questa parte. So, welcome everyone. Thank you for coming for the third lecture. So here I wrote a small summary. If you just to refresh our memory about what we covered in the first two lectures. So the first one, we spent a lot of time on an almost trivial theory, well, actually on a trivial theory, which was the free scalar. And but I use this to motivate the fact that symmetries would be characterized by either of these two facts, either the ability to couple the theory to background gauge fields, which have some gauge symmetry, and the partition function is invariant under this. This is provided there is no anomaly. I mentioned it several times. I will again mention it today, but still not cover the anomaly. This is for next time. Or the existence of topological operators, which are defined on codimension 1 submanifolds and labeled by the group. And when these operators are put together, they fuse according to the group multiplication. The first one. And then in the second lecture, we looked at some slightly more involved examples, the compact scalar, and which is almost trivial, and then free Maxwell, which is a full-fledged gauge theory. But then we saw that these were very, very similar theories, actually, at least formally. They are given by an action, which is, again, it's the same thing, except you replace all the zeros by ones. In the compact scalar, the fact that it's compact means that phi is equivalent to phi plus 2 pi. You can add any multiple, integer multiple of 2 pi. And we saw that formally this is very similar to the whole gauge invariance of Maxwell theory, where you can also shift A by d lambda, where lambda is any function of space-time itself subject to an identification like this. And then we studied symmetries of these theories, and then we saw, actually we started with the compact scalar in 2 dimensions, which had momentum and winding symmetry. Then if you want to do it on any dimension, d-dimensional space-time, then if you want the thing to be continuous when you vary d, you have to extend your notion of symmetry and accept that it's not always codimension 1, it can be codimension p plus 1 for any integer p, and then the background gauge fields are not 1 form, but p plus 1 form. So the previous thing was the p equals 0 statement, and now we replace with arbitrary p. And then we had that momentum is a 0 form symmetry, so p equals 0. But winding symmetry is with p equal d minus 1. Minus 1. Let me compute because it should be 0 in. Maybe I copied this. But I'm not right. It is now. 0, yeah, the chart operator should be dimension p. Here I will. Here's d minus. Okay, thank you. Yeah, these two numbers add up to d minus 1 always. So the symmetry defects are d minus 1 supported, so that's normal symmetry, and then the chart operators were just this exponentiated field, compact scalar. And then for the winding, this is p equals d minus 2. And then we saw that the charge operators were this kind of vortex points according to dimension, but then lines in higher dimension and so on. And the analog of this for free Maxwell was electric and magnetic symmetry. All of this symmetry are U1. And this is p equal 1. And this is p equal d minus 3. And here I also miswrote. And so we have the chart operators are the Wilson lines, which are the holonomy of the one form gauge fields, and the TOF, which are the analog of this, but for one forms. So they are kind of the insertion of monopole operators. I don't remember if I had time to properly define the TOF line, so maybe I will just write this now. And then the symmetry defects are supported on the manifold of these dimensions.
Do your symmetry defects come with a U1 parameter like your UG?
Yes, sure. So I think I wrote them last time, but we can. again, because everything is U1 here. For instance, because it's U1, we can use the language of Noether current. So in this case here, we had the electric current, which was the two form, which was basically the F to dA was JE, and then the Wilson this symmetry defect here is UG of sigma d minus 2. And that's just the exponential of I alpha and alpha. So G is e to the I alpha. And then this is the integral of sigma d minus 2 star J. Electric. Then you have the same with magnet. So there's a continuous parameter here. And then we actually discussed the fact that if alpha is an integer multiple of 2 pi, that should be a trivial operator because of this side. And indeed it is because this thing here is quantized. When alpha is a multiple of 2 pi, this would be a trivial operator. Okay, so that was the content. And well, so as we saw, we have to generalize this definition given in the first section. So this is what I want to cover today. So the plan today, there's maybe more than the other times. So I will write what I plan to cover, and then we see what we get. So I want to, in the first part, well, just give the definition of the higher form symmetries. The general thing where basically it was written here, but then study some of their properties. And then, as I promised at the beginning, each lecture is based on a theory, an example, to have some concrete idea of what's going on. Here it was the free scalar, here it was Maxwell. Now we grow in complexity, and now we will try to cover Yang-Mills theory. But before that, I want to explain a bit more what gauging is, because that will now play a more and more crucial role. And then in the third part, to apply all of this to Yang-Mills, which is a Abelian version of. Okay, so that's the plan. But if you have any questions, sure. So I will basically copy this, except so today I will almost not use the background gauge field language because it will be easier to draw a picture with topological operators. In principle, everything can be translated, but today I will mainly use these drawings. Next time, when we will, just to say where we are going. So this is for today, and then later we will start mixing things of different degrees. So today we are not really covering this, and we're not really covering anomaly. Next time will be that we mix everything together. And then for sanity checks, I will come back to the background gauge field next time. But today it will be mostly topological operators. So, so just let's give a definition of what these higher form symmetries are. So we take G, let G be a group, any group, and then we say that a theory has a symmetry, well, higher form symmetry, H, higher form symmetry, G, P. So I use the same notation as for the form. So I put the group and then I put P in brackets as an exponent. It doesn't mean anything else than to say that this group, that's just the mathematical object group, will play the role of the P form symmetry. So has higher form symmetry GP if, I should say, actually, let me non-anomalous higher form symmetry GP if there are codimension P, dimension P plus 1 operators UG of sigma G minus 1 for G in the group, sigma closed. And let's just repeat this with fusion. So that's our definition. Yeah, so we'll work with this. Again, in principle, there is this this other version as well. Let's work with that. And okay, let's now extract from there some of the properties. So here I said, okay, G can be any group, but very quickly we see that there is a fundamental restriction on the groups that we can use actually. Also today, because as the complexity increases, I will be slightly less explicit than the other previous times where I could really prove everything and do the computations in detail. So sometimes I will be a bit more sketchy, but in principle you can follow. If you are worried that something cannot be done, then you should ask me and we can try to do it in detail. Okay, so the first fact that I want to stress, fact 1. So if P is larger or equal to 1, so for actually higher form symmetries, of course this terminology is a bit redundant, we see 0, but we still put it together. But then if P is larger or equal to 1, so it's a true higher form symmetry, G is abelian. That's a very important property. And we can prove it in a very straightforward way using these operators. So how do you do that? Well, let's just make a drawing, which hopefully is clear. Let's look, for instance, in 2 dimensions. So in 2 dimensions, it's small. A one-form symmetry in 2 dimensions, if you go back to the definition, means that we are codimension P plus 1, which means codimension 2 topological operator. So they are just points. So in P equals 2 and P equals to 1, then UG is supported on a point. So okay, I can put UG here, and then I put another UH here. And then I'm told that fusion respect the group law, so that should be equal to, I put them all together and I get UGH. But then of course they are topological. Oh, sorry, I think I forgot the essential word here. Topological. Sorry. Did I forget it here? No. Right, topological. So yeah, so I should repeat that whenever I make these drawings, it means within a correlation function, you can evaluate those things and they give the same within correlation. So topological means, okay, I can move them around. So that's also equal to UH, UG, just because I have enough room. And then that's UHG. And we have proven that UGH and UHG are the same. So the group is abelian. And then if you want the proof for higher P and higher P, well, it's just the same thing, but you extend with how many dimensions you like. So, for instance, if you're in 3 dimensions and you have P equal to 1, now you have lines, but lines in 3 dimensions can also be exchanged. The reason why this doesn't work for P equal to 0 is because when you have P equal to 0, you don't have enough room, you see, to exchange things. So let's say the topological reason if you want, is that the sphere in P dimension is connected, so you can go around, except in 0 dimension, where the sphere is 2 points. SP is connected if P is larger or equal to, and not equal to. So that's a kind of convoluted way of saying Okay, so we are restricted to abelian groups. So it's good in a way because it will simplify our life. And also bad because we might want to have non-abelian higher form symmetries. If we want to do this, we have to wait for next week. Friday. Actually, the next lecture is on Friday. Okay, so that was fact number one. Any question about the argument here?
Sorry, you actually proved that it is the representation which is non-abelian. Usually the representation is homomorphism, but is a faithful.
Well, okay, yes. Right. So there is this this thing of faithful. It's a good point. I didn't emphasize too much because sometimes it's an overkill. But of course, every symmetry that I mentioned here should act faithfully on something, because otherwise I can say that SO1000 is a symmetry of any theory, which acts trivially on everything and doesn't really.
Okay.
So, but here I don't even need that, because here these are the symmetry operators. But it's just that if when I say something is a symmetry of a theory, I need to have at least one operator that transforms non-trivially. Otherwise, everything is a symmetry of everything. That's the point. But I'll now come back actually to the question of representation. So what really transforms in representations are the charged operators, as we are used to. So we will come to this. So, but there is first another fact which is very related to that. So fact number two. We should put some color around them. Number one. Now number two is G, P. So if I have a higher form symmetry, cannot act on operators supported in dimension which is lower than 2. Second fact is almost as trivial as this. Okay, let's just make some drawing. Let's do d equal to 3 just to have more space. And let's look at the different kind of operators and different p's. So I can start with p equals 0. So I have a 0 form symmetry. But okay, there is no dimension less than 0. So I cannot say anything. So let me start with p equal to 1. So the claim is one form symmetries cannot act on dimension 0 operator. And okay, let's see how it works. So we are in 3 dimensions. P equal 1. So our symmetry operators are codimension p plus 1, which is 2. So the operators are lines. So maybe I should pick a color for the. Maybe I try to do in red the symmetry operators. I don't remember which color I picked. So the operators are like that's a UG, for instance. Now, can it act on a local operator? Well, even if I try to put the local operator here in the middle, because it's topological, I can deform the loop. You see, the loop cannot link with the point. So that's obviously the same as I put O here, and now UG is over there. I can send it at the universe if I want to, so it doesn't act. Right, that's it. And you can do this with any dimension, just not enough to link. So the proof, the topological argument is no linking. Okay, so then on what does it act? Well, this bound is sharp, meaning that on dimension p, it does act. And actually, it can act on any higher dimension. Like dp can act on operators supported in dimension larger or equal to. So okay, let's do again the same thing. P equal to 3. If I have p equal to 0, I can act on the zero-dimensional operator. How? Well, that's the linking thing. So you remember we saw it the first time. That would be a sphere. That would be UG supported on red. An S2, and I can put a UG on that. Then I can put a local operator here in the middle, and it wraps. So you always have two ways of seeing this. Either you say that the sphere contracts and kind of eats the operator, and then there's an action. There's the action of the element G on the operator O, which still sits somewhere here. Or the other version, you can also make the sphere very, very large, and then at some point you have to, or not large, you just take it out, and then the operator has to cross the surface, and that's what we saw last time, that the group acts when we have such a thing. So either way, you're right. So this is p equals 0, and dimension is local. If you have p equal to 1, we have now a situation here. Right? That's the UG. It's defined on S1. And now we are acting on a one-dimensional operator. So that, and these two things can link. Yes, and then yes. What's the question?
Yeah. So would you say is it the same or is it different?
Yes, cannot act means acts trivially.
Okay.
Again, I have this notion that to me act means non-trivially, because otherwise everything acts. Yeah, so p equal 1, you see that a dimension 2 operator can wrap a line. And so there will be an action. There is no way to disentangle this without having some topological. Right? If I try to undo them, at some point the two lines will have to cross. Okay. So that's the easy thing. Now, in principle, comes the question. You've done p equals 0. So let me call q the dimension of the operator. So this I call q. So I say that q has to be larger or equal to p. So that's p equals 0, q equals 0. That's p equal 1, q equal 1. Now I should look at other cases. For instance, q equals 1 and p equals 0. So can I act there? Is there a way to have an action of a zero form symmetry on a one dimension, so on a line? So zero form symmetry is this thing, surfaces. Can they do something on a line? Yeah. Yes. We can take a line, and then we can wrap a little cylinder around. Yeah. And then that will the cylinder collapses on the line, so it acts on the line. So that's possible. And if we take q equals 2 and p equals 0, now we want to act on the plane. Well, do the same trick. Now that's the plane, that's our operator is two-dimensional, but then still p equals 0 can act. I just, for instance, I just put it there, my surface, and then I say that it acts by crossing. Or if I want the same picture as this, I say I put one on each side, and I say that it acts by sandwiching. So you see the point is I can put my UG. So here I did an S2. Here I put it on S1 times the support of this. So if this was supported in gamma 1, this was an S1 times gamma 1. And here, if this was gamma 2, the UG is on S0 times gamma 2. Again, S0 is 2 points, so we take 2 points. So yes, it can act, but this is again sharp. You cannot improve it. It does not act when it's strictly lower than P. It acts on everything higher than P. I should also maybe illustrate how P equals 1 and Q equals 2 work, or maybe draw it by itself. If you have Q here, P equal 1, Q equal 2. So now I have a two-dimensional operator here, and then P equal 1, so I have some kind of lines. But I can, again, it's a bit less obvious what it's doing, but I can have a line here and another line on the other side. You see that there is no way to disentangle this apart from having the line cross the surface. So there will be some action. I have not said which action at the moment. That's it. Any question on that? So that's the first place where we depart a bit from the original papers. So in the original paper, here there was an equality. It is said that the P-form operators, the P-form symmetries, they act on dimension P. Then later this was improved, so I should just give maybe a reference. And I will give the reference now. Where did I put it? Yeah. So 23. So actually, it's not that old, as you can see. 2304. 260 by Lakshya, Bhardwaj, and Sakura, Shatan, and Miki. So they have a paper called Generalized Charges, which explains this. Okay, so we are now going to explore a little bit things that are in this paper, and that's how this thing acts. Like, what does it mean? I have just said that it acts, but I was very vague. Now let's be a bit more precise. So the question is, basically, how do they? This is the first point where I have a kind of a decision to make, whether to explain, like in which way to explain things. So first of all, some vocabulary. When you have a symmetry, let's go back to the usual thing. You have a symmetry, act on local operators. Then you say that if it does not act, you say that it has charge 0. If it acts, you say it has some charge. So the way a symmetry acts on an operator is we call the charge. And now this question can be rephrased in this language as what are Q charges? What are Q charges for VP? Okay, that's okay. So maybe I explain a little bit about the structure. So we will uncover this as we go in next time, and even more the time after. But I just need to introduce this a little bit now. So we have a theory, and let's say we say that there is a P-form symmetry on it. That means that there exist all these operators. So for instance, let's again draw D equal to 3. Again, now I will be very vague, and I will try to be more precise next time. But let's say I have a one-form symmetry. That means I have a bunch of codimension 1, which means line operators. A bunch of things like that, UG, U, G prime, and so on. What does it mean to say there are those things? Well, the idea is we can say the idea is we can go inductively in the dimension of those things. So first of all, when we started with zero form symmetry and we said there are codimension 1 operators, which means surfaces, a way of saying this is to do the following, is to say, let's assume I have my theory. So my theory is defined in 3 dimensions. So I have let's say that this is my 3-dimensional volume. The theory is there. And then what does it mean to say that they are symmetry operators? It means that they are this codimension 1, so kind of slices here, which are a symmetry of the theory, which means on this side I have the theory, call it T, and on the other side I also have T. And then I ask, what are the codimension 1 operators? So what are the things I can insert so that I still have T on both sides? So that's a bit abstract, but that's one way you can phrase it. And the way I say this is because there is one thing which is always there, which is there is an identity operator. When G equals 1, the trivial group is always asymmetry, and so there is always a trivial thing. So if there is a trivial, so even if there is no zero form symmetry, we say there is no, but there is always the trivial group that is there. So there is always the trivial surface. And then when there is the trivial surface, I can ask what are the symmetries within that trivial surface. So now you have your theory like that. Again, let's assume there is no zero form symmetry. That means there is only the trivial thing. So I put it in yellow. This is maybe not distinguishable from white, but that's on purpose. So this is almost as if it was not there. But then I can ask recursively, what are the codimension 1 operators in the yellow thing? And now these would be lines. But from the perspective of the big thing, now they are codimension 2, right? Because I've iterated the question. Then I can go on. Even if there is no such line, there is at least the identity one that does nothing. Then I can ask on that line, what are the operators that there are? And if there are some, then there would be points. So there would be 2 form symmetries. And I can keep going like that in dimension. Well, here I have to stop at 3 because I took d equals 3. But if you take d equals whatever, you can iterate this question. For each operator, you ask what are the symmetries of it. Why do I say these things? The reason is it makes a structure that emerges. What is the structure? The structure is we started from the theory. The theory I can put, so now I will draw some abstract diagram. So there is the theory is here. And now I ask, what are the codimension 1 operators? And codimension 1, you see they have T on one side, and they also have T on the other side. So one way to denote them is I can kind of take the dual picture of that. In graph theory, you have the dual. You replace every face of dimension D by something of dimension the opposite, and so on. So the dual of this picture, you see, would look like something like that. You would have T, and here you would also have T, and then the thing would be an arrow. Yeah. But because it's T and T, I can draw this as the arrow going. So you see, I have arrows like that. These are the symmetries that act on T. Quite legitimate to present the symmetries like that. Are things that act on T. But then with this language, you see that here the red line within so the yellow thing is a symmetry. So it's a thing like that. Maybe I should have kept the color actually. Let me keep red. This I keep it as red, and now I put the yellow in it. And you see now I have a symmetry here and another here, and then yellow is exactly the same. So it goes from, for instance, this arrow to this arrow. Since I will draw it like that. And then to denote that the codimension is now 2, I put a double arrow. Of course, I could have also, maybe we have examples today with the mills, examples where on this side I have a particular UG. Maybe here I have UG, And here I have U G prime. And now this thing is a junction between the two operators. If I have this, then this would be an arrow that would kind of go. And then if I inserted, let's say, a point operator here on the yellow thing, then that would be, you see, a codimension 3 thing that acts on the yellow, and you construct like this. So you might be confused, actually, why is there only one theory at the beginning? Indeed, you could put also more things here. You could say that I just not want to focus on symmetry defects, but maybe just on any kind of defects which would be interfaces. If you do this, there would just not be only one theory, but several theories, and the red arrows would also go from that to theory here and so on. So why do I say all this? Because we will use this picture a bit later. But I need that for one thing. So there is a well-defined question. How does this inductive procedure work? It works as follows. So the inductive procedure works by asking repeatedly the question, given OP, so I take a p-dimensional operator and another one, it's called tilde p. I take two p-dimensional operators. What is the set? And it will be a vector space, because whenever I have an operator, I can always add another one and make linear combination. So what is the vector space of operators of p plus 1, sorry, p minus 1 dimensional operators joining them? So that means given UG prime, can I join them using a one-dimensional lower operator? And I ask this always as soon as I can, as long as I can, and then until I cannot ask anymore. And then I record all the answers to all of these questions in a diagram like this. So, so those who know have recognized that here we have a category, actually a higher category, where we have objects and then morphisms and morphisms between morphisms and so on. And that question can be rephrased in the categorical language as, what is the set of morphisms from OP to OP? Right. So I will not use this too much now. I just need one thing. Let me just mention one thing in case you're lost with this diagram. We will basically not use it, because what we're looking at today is the diagram of this one, but a very simple. So, what is a theory with a zero-form symmetry? How would I draw this in this language? Well, it has zero-form symmetry, so there is a theory. Then there is a zero-form symmetry, so there is a bunch of red arrows, like that. G1, G2, G3. And then that's it. I don't have any more codimension. This kind of zero-form symmetry. I don't have to add any of the higher colored arrows. So secretly, they are still there. There are some of them. Which ones? The identity, because the identity is always there. So each red arrow is decorated by a little arrow here, which is the identity. And here as well, identity. But because it's so trivial, I can just ignore them. Also, each of the yellow one will be decorated with a blue one and so on. And it continues until the end of the dimension. But I can safely ignore all of this. So I just don't draw that. So that's the picture. And then what did I assume? If it's a zero form symmetry, it means that when you compose the arrows, you just get the product of the group. And in particular, in a group, every also there is the identity. It's somewhere. Yes, let's write it as identity. And then in a group, as soon as you have an element, you have some inverse element somewhere. So maybe G3 is the inverse of G1. If I compose them, I get the identity. This ability to compose and get the identity means that everything is invertible. That's part of the definition of a group or a symmetry. So that's just a normal group. And indeed, a group is the same thing as a category with one object and all arrows are invertible. Again, if you don't know what categories are, they are just this kind of diagram. They are objects and they are arrows. And then if there is just one object and all the arrows are invertible, that's exactly the same thing as a group. So that's just a fancy way of denoting a group. So that's the zero form symmetry. And now let me just write what is a higher form symmetry. So just theory is a one form symmetry. It's almost as trivial. If there is one form symmetry, it means there are codimension 2. So it means in particular there is nothing of codimension 1. Otherwise I would have said it has zero form and one form. So if there is just one form symmetry, there is the theory here. Then in the zero form symmetry is triggered, there is just the identity. Then there is my one form symmetry group, which is doing things here. And you see it's exactly the same picture as this, except it's one level lower. And exactly in the same way as here I ignored all the higher color things, here I can ignore all the lower color things. So I could safely ignore that these actually go from identity to identity, and then I would just recover a group. So in the end, a high form symmetry, it's just a group, but which in this general pattern of all the defects is located at a certain height in the full vector. Let me just mention one thing. I didn't want to spend too much time on it. Just one thing. How can we prove using this that the group is abelian? It's the fact one that I erased. You can have a very simple proof which kind of reproduces the topological one that I gave before. How do you do this? Well, you just use the fact that when you have these higher morphisms, there are several ways of composing them, just because of the way they are. So maybe I should postpone this for. Let me just draw it. Again, the goal is to not give all the axioms and so on definition for the categories at this point, just to draw a picture, but to show that it's exactly the same. Actually, so if you understood what I just erased, you also understand this. How do we show that the group is abelian here? Very easy. If the group is abelian, means let's say that this one is G1 and this one is G2. And we want to show that G1, G2 is the same as G2, G1. How do we do this? Well, first of all, let me draw this in a slightly better way, more readable. I can say that G1, so this point, which is only one, I just write it twice. It's the same thing, but it's as I did here. It's a bit simpler to denote it like that. Then I have only the identity that goes between those things. I can put the identity here, the red. That's the right one. Here's the identity, and here I have my first element, G1. Put the arrows this way too. So all the red arrows are always the identity. And then I put again the identity here, and then I put G2 here. And remember, what is the meaning of this? You take the dual of everything. So the point becomes a two-dimensional. Let's imagine we're in 2 dimensions. The point becomes 2-dimensional. These red things become 1-dimensional. You see, the dual picture of this is that. It's a red line, but remember it's the identity, so as if it was not here. And then this is G1 here, and this is G2 here. You remember at the very beginning, I showed that when you have this, you can just swap them. It was obvious topologically that you can swap them. Because again, they are on the red line, but the red line is nothing. It's the identity. How do I do this in picture? Well, I can just say that this is the same as I can compose everything with the identity. So I have G1, G2. Now here I put the identity, and the identity, like that. And then actually I could have composed it. If I have this, I have identity, identity, then I can multiply. Like this is as if I put another trivial line here with nothing, and here I put the identity operator here and here. It's obviously the same as this. I've done nothing. But I could as well put exchange identity and G2 here, with the identity here and G2 over there. And now I sandwich the picture this way. So I have this. And now I have G1 here and G2 here. You see, I've done the move of kind of moving things a quarter of a turn. And now, of course, I can repeat this because nothing told me that I should do it with G2 and not G1. I could have done it with G1 and G2. So then I would have this picture with the things reversed. And then I can keep doing. And at some point, I will arrive at this with 1 and 2 exchanged. So you see the ability of swapping the operators is here manifest in this combination of arrows. Just an example of how we can see the physical statement that the higher form symmetry groups are abelian from kind of that. Here it's a bit of an overkill because we saw it in this way. Is this clear? Why am I saying all this? Remember, we want to answer the question which is up there. The reason I'm saying this is because in order to answer this question, we need to specify a bit which operators we're talking about. And there are operators which are called simple. What are simple operators? Let me define this. So we say that an operator, O, T, the p-dimensional operator, is called simple if, well, remember, for every operator I can ask, what are all the insertions I can put on it? And if this is as small as it can, we call it simple. So if I write it in this language, it will be from OP is one-dimensional, which is equivalent to only your identity p minus 1 operator on O. That's what I mean by a simple operator. Right? So if I have, so if p is 0, that's trivial. Like I have a point, I cannot insert anything else. But if I have a line, I could very well have a line which itself has a symmetry. In a way, that's the symmetry of the operator. A line could have a symmetry if I can insert operators on them. You know, I take the definition that we saw in the first lecture. I have a line, so I mean, one dimension. Does it have a symmetry? So does it have topological operators that I can move around? And if it does not, we say that it's simple. So let's illustrate why this is important. I guess this is will be my fact number. So the answer to this question. So all of this detour was just to answer this question. So now let me erase all of that. And the detour was motivated by first the fact that we will use this in the last lecture, but also that I don't know how to define this properly if I don't have the language. Okay, so now the statement is number 3. Simple, genuine, identical operators for P, they transform, and GP, a representation of, you'll be disappointed, that kind of trigger statements. So I'm just saying that now if you have p-dimensional operators, actually, what do they represent? What do they? How does G act on them? Well, it's just they are representations. So exactly what we knew from the case P equals 0. So P equals 0 means a normal symmetry. It acts on operators as representations. Okay, maybe that's a bit disappointing, but actually it's very non-trivial, and a lot of things are hidden in here. First of all, I've defined the first term here, simple. Defined here. There's another word here, which is genuine. So what does genuine mean? Genuine means that the operator should be able to live its own life. That's the unwavy definition. The technical definition is this operator should appear. It should be on the identity of one dimension phi. So, for instance, if I take my pictures from before, I had in red, for instance, I had some symmetry defect. I can label this by G, and then I can put the identity, which I don't draw, on the other side. And then on the head of G, I can put a yellow one. Right, so G here goes to infinity, but then at the end of it, there is an operator. You see that is attached to G. That is non-genuine because it is not free. You know, it's technically it's in the home of G to the identity. It's not in the home of identity to identity. So that would be non-genuine. Everything we've seen up to now, they are genuine. So that's why focus on genuine, simple. And then I claim that if there are these two things, then we just are dealing with representations. How do we prove that? Again, I'll make some drawing, and I guess everything should make sense with this. So let's again prove this. Let's say p equal to 3 and p equal to 1. So p equal to 1, the operators are line, and charge operator is a line as well. So I draw it like that. A line linked by the. Now, if I want to unlink, you know, in the 20 minutes ago, I was a bit vague. I said, okay, you don't have you have some topological linking, but I did not really explain how it acts. Well, now we know how it acts. We can undo the linking. Now that's the same as the line would be here. This circle would be here, and then at the point where they cross, there could be something stuck on it, because there was a non-trivial topological operation which happened in 0 dimension. And there could even be maybe something that remembers that it came from linking, something like that. So, but because we're talking about genuine operators, that thing is not here. So nothing here because of the genuine assumption. And now because of the simple assumption, here we have our line, so let's call it L. So it's L everywhere. Now it's kind of split into two. So it could be that something has changed. But of course, the operator acted locally here. So this is L, this is still L. And therefore, this thing here, which is, it's a topological operator, because I could have put my red loop anywhere and moved it, and it would have given the same thing because of the topologicity of the red thing. So then the yellow thing is also topological. But then it's simple. There is no topological apart from the identity or any multiple of it. Right? It's one-dimensional vector space. So that's the same as just the line with nothing inserted. That thing is still here, but I can forget about it. And now I have a number, the proportionality between this and the identity, which I can call, say, rho. And it depends on if this was UG, it depends on G. And that's it. Remember, these drawings are within correlation functions. So I've just shown that if I unlink, I just multiply the whole thing by rho of G, which is some complex number. Zero complex number. And then by doing, if you put two of them, two UGs, and you do this several times, and you can use the very trivial topological move, you see that rho of G satisfies the group law, so it's actually a character. So rho is a character. It's a one-dimensional representation of the group, and of course this is expected because we are dealing with an abelian group, so the irreducible representations are just the character. The rho is in G hat, so I will introduce this notion. G hat is just called the Pontryagin dual group, just the same thing as the group morphism from G to U1. And these are the same thing as the irreducible of G.
You didn't say it was irreducible.
I didn't say it was irreducible, that's, but I think simple implies it. So the simple, I could, okay, if you want, I could add it as an irreducible. In other words, a character. So you might say, okay, all this to say that the P charges are the characters of G. But you see, I very safely evaded another case. You remember in the fact number 2, which is erased now, there was the possibility of having higher dimensional operators still charged under GP. You might ask, what do these transform in? Like, what are the Q charges? And okay, in view of time, I will not answer this here, but I'll just give it as a fact 4, but not explained. Maybe we come back on it the last lecture, but maybe I should not even write it. Just write it so that you know. So you can refer to this paper I mentioned above. So the Q charges of GP, they are one. They are so-called 2+1 representation of the P+1 group phase and what does this mean? Just in a sentence. There is a notion which generalizes that of representation to higher representations, so that's what these things are. When Q equals 0, that's just a normal representation. And then what is the P+1 group based on G? Well, that's this construction that so you see that's technically that's a 2 group, because I said a group is a category with one object and all the arrows are invertible. Here is not that. There is only one arrow here and all the arrows are at level 2. So that's a 2 group, but a kind of rather trivial 2 group because it's actually just a group in disguise. So that's the 2 group. That's the 2 group base. And okay, there is a notion of what representations of this mean, but I don't want to answer this. But just the drawings that I drew at the beginning, where we had, for instance, when we had this, we had a zero-form symmetry acting on a line. And I drew this, and I said, like hand-wavingly, I said, yeah, the cylinder can wrap on the line and then it acts. If you believe me there, you might have complained. Definitely, it will not be a representation of G. Why? Because there is much more topology in this drawing. For instance, you could say, oh, but what if the line actually crosses the crosses it? So for instance, there is a possibility to have something like that. And the line crosses here, and maybe the line changes in nature. See that as a difference from here. Here, this was L and L on both sides, because the crossing was local. Here, if you want to go from this configuration to this, all of the part here has crossed. Maybe that was L, the same as here, but now that's another thing. No guarantee that it's. So even if the thing is simple, now these are not the same thing. So here, there will become operators stuck there. And there's a whole story there. Let's discuss more now. But, this. And before the break, there's a question about this. I want to arrive at the last fact that I want to give about the general structure of the hypercontinuities. One, let's call it 3 prime. It's just a generalization version of 3, but since I have not really covered it, I don't want to too much. But then fact 4 is important. And then we move to the application to Young Miss. So the fact 4 is a practical way of how to compute those things. So question. How to compute GP in practice. In practice, I mean, I give you a theory and I ask, what is GP for any P? There is a recipe, with unweighted, but I will try to motivate it with the study of Maxwell theory. Let's say, so motivate, I motivate, and then I will give the answer, and then we do the break. Motivation. I start from Maxwell. We covered Maxwell in some detail last time, and we saw that there were these Wilson. I think I called them W. They were labeled. There was an index n, which charged the Wilson line. Remember, Wilson line Wn on some path gamma. It was the exponential of I n and the integral of A over gamma. What's the definition? And okay, you have those lines, and there is one for each n, there is one. And there is no way in Maxwell theory, okay, now we have a concrete way of answering this kind of abstract question. Is it possible? Well, is there something that we can add on Wn? Is there something here that I can put that will be on Wn? Well, no, you can check. You need gauge invariant operators and so on. There's just nothing. There's almost nothing you can do which is gauge invariant. Basically, there is only Wn. So it's also not possible to add something here and then to go to Wn prime if n prime is different from n. Whatever you do, this will be non-gauge invariant. Again, I say it's a bit unweighted because I cannot prove that I cannot do it. I mean, I would need to go through all the operators and so on. In Maxwell, it's probably doable because it's so simple, but then in any non-trivial theory, it will be hard. But okay, we can scratch our heads, and then at the end, we don't find anything. So we say that this is not possible, doesn't exist. So this fact that we cannot put anything here between two Wilson lines of different charges, we say that Wn cannot be string. This word string, the important one. I will define it in more generality in a minute. We give an example where it can be string now. So let's say that now we look at not Maxwell theory, but we look at QED. What? Now, we look at QED. So QED is Maxwell with some electrons. And now, as you know, if you have an electron sitting here, the field that creates an electron, the creation operator of an electron. Now, this is not gauge invariant by itself, but it sits at the end of the Wilson line of charge 1. And this configuration is gauge invariant, and that's so as you can see now, W1 can be screened by the electron. And then by using this basic building block, you can actually screen any n and n prime. Essentially, by putting the right power of the electron field, you can go from Wn to Wn prime for any n and n prime. But now let's look at the consequences of that. You remember that these are the charge operators for the one-form symmetry. One-form symmetry is measured by linking something around that. And by linking, if we evaluate this, it gives n. So here, the fact that you cannot screen it means that indeed the charge is well defined. It's n, and if I move around, it's topological, so I can move and I will still measure n. I cannot measure a different n prime. While here, if I try to measure the one-form symmetry around here, put the loop, but you see I can just move the loop here and unlink it. So the charge at the one-form symmetry has to be 0. This is not charge under the electric one-form symmetry. So the electron has realized an explicit breaking of the one-form symmetry. Just because what was charged before is now not charged. So here in Maxwell there is a U1 one-form symmetry, unbroken. I mean, we will see that it's spontaneously broken, but not explicitly broken. Here there is no electric symmetry. Why? Because the only charge operator will have this Wilson. But even the one with charge 1 is not charged actually. So there is nothing. There is no electric one-form symmetry. Okay, and last exercise. I will not even do it because it's I will give the answer because it's very trivial. Let's say we have QED, but now we don't have charge 1 electron, but with charge n electrons. Then what does it mean? It means that the electron can sit at the end of the charge n Wilson line, but not charge 1. So then you see that you will be able to connect two Wilson lines if the difference of the two charges are divisible by n, but not otherwise. So then the symmetry, what can you measure with the one-form symmetry? You can just measure the n-ality. What is the charge modulo n? Because each time you find n, you can screen it away. So there is a z n one-form electric symmetries. So all of these examples are supposed to illustrate the general answer to that question, which I gave as now my fact 4. And then first I need to define. So we say that an operator OP can be screened to another operator for tilde p if there is a p-1 dimensional operator between them. Let me not even write it, let me just make a drawing. So we have OP. Let's say OP is a, let me draw it as the surface operator, for instance. So this is OP over here. And now there is OP prime, which can surround it. So on this, there is copy tilde, sorry. And then you see there is a junction here. This is the p minus 1 dimensional operator that screens it. And it really means screening, because if there is this one in the middle, but you're very far, you just see the blue guy. It's screened by the blue guy.
Sorry, so if it cannot be screened, you always say that it can be screened in a larger theory?
It cannot be screened. And it is in a large, yeah, you mean by adding more operators? Yeah, sure. So that's what this example shows. So in, for instance, if you have, then you don't put an electron, but the mass is actually super high. You're in the area, then you think that there is a U1 symmetry. But then if you go sufficiently high, then this U1 can be screened by operators that will be sufficiently high in energy. So yes, you can complete it. If it's UV complete, then you know. And so, okay, now we have the screening. And now, if you put all these computations together, you are supposed to understand that the Wn, remember, they are charged things. So they are in that group, right? The charged object, they are in the dual of the symmetry group. So then the statement is, GP is equal to what? You take the set of all two-dimensional operators. These are all possible three-dimensional operators. You mod out by the screening relation. That's an equivalence relation, so you can mod out. And then, in the good cases, this will be a group, a Billian group. And then we have to undo this, which is here. Okay, that's that. So, in words, you look at all three-dimensional operators, and you screen them as much as you can. And then those which you cannot screen, like for instance here, you could not screen the charges which are not divisible by n. And then what is the group created by them? Well, it's Zn, and the dual of Zn is Zn. Okay. In Maxwell, you find that you cannot screen anything. So then you have that the charges of the Wilsonites are just all the integers. What is the dual of the integer? It's U1. You recover U1. And in this example, you find nothing. Any question on that? Yes.
Here for P groups, you mean like this P plus one?
I mean, just the characters. So the characters of Z are U1, characters of U1 are Z, and then if the group is Zn, then it's Zn. Which is a group. Yeah. Here I'm a bit, you could complain. Actually, no one is complaining, but could complain that maybe this is not a group. I have not really defined this relation. You know, I said at the beginning that there will be some unwaviness today. So it begins now. But look, morally, this is true, and this will, for every intents and purposes that we will need, this is good enough. Okay, if there is no more question, then now we have the break. Okay, so yeah, so that concludes my first part on the general description of these high-form symmetries. Maybe one thing that I should repeat: why is this true? I just erased, but the reasoning is really if two things, like if OP and OP prime can be screened to one another, that means there is something that can connect them, then you see that there is OP and then there's OP prime or tilde, then obviously they have the same charge. Because if you measure the charge, you measure it by linking something here, you move it here, they are the same. Right? So that's the argument. That's why this holds. And because we want the symmetry to act faithfully, we want something to be charged. So if you don't have anything that can distinguish, if these two things have the same charge, from the perspective of the symmetric group, they are the same object. So that's why you take all the p-dimensional operators, and then you identify any two which can be screened to each other. And these are the actual charges. And since the relation between charge and operate and group is this dual, that's why it happens. Maybe a bit too fast. Okay. Any question on? Yes.
In QED, then there are one-dimensional operators, but no one-dimensional charge. Or no.
That's right. Yeah, in QED there is. So okay, in Maxwell, there were two symmetries. There was U1 electric, and there was U1 magnetic. Now, if you do, and these were the Wilson lines, and these were the torque lines. Now, if you add electrons, so in QED, now the Wilson lines can be screened by electrons. The torque lines cannot be screened. There is no magnetic monopole, dynamical magnetic monopole that you can insert here, and that's what you would need to screen that. So in QED, the symmetry is just U1 magnetic.
So the operators are still there, but they are screened, so there is.
The operators are there, but yes, exactly. The argument is the Wilson lines are still there, but they can end on the electron field. So if you try to measure their charge, you move this away, and that's 0. So you can say if you want that this is still there, but it acts on nothing. And by our general principle, something that acts on nothing, everything acts on nothing. So you just remove it.
Does it act on closed Wilson loops?
Yes, but again, this will not be stable dynamically because the closed Wilson loops can be opened by pairwise creation of electron and anti-electron, so it will decay.
So you're saying that if you add a magnetic monopole, then you're breaking your remaining one. Yeah. Symmetry left.
That's what we would see in QCD. QCD will have no symmetry. Makes sense. So, which has implications. So I want to say a few things about phases of gauge theories and Yang-Mills and so on. But first, I had my plan at the beginning, and there was this section 2 about gauging. So I still want to say a few words about gauging. That was my second part. So gauging. So I already mentioned this at the very beginning, because there is we're talking a lot about symmetries, and I emphasize very strongly that what some people call gauge symmetry is not a symmetry. You just saw it. I just said that QCD has no symmetry. So the process of gauging is very important. So what is it? I need to write it at least once. So we take a theory with a symmetry, and again I have to say a non-anomalous symmetry G. So in the old days we would just write this. Now we write GP here, because the whole motto of this generalized symmetries is that everything you can do with normal symmetries you can do there, but in particular you can gauge them. So you take a theory with a symmetry, and now gauging is the process that constructs for you a new theory. So you can decide to gauge the symmetry, and now you obtain a new theory. Gauge theory. It no longer has the symmetry GP. If you apply our definitions from before, if it has the symmetry GP, it means that there are these topological operators and so on. In that theory, they are not there anymore. Because what is gauging? Well, I have not said what it is, but I think I said it maybe last time. Basically, how to do this? How is this process done? Well, we use our definition. The fact that we have a symmetry means we can couple the theory to background gauge field. So you couple to background gauge field. So now the partition functions of the theory depend on B T plus 1, which is the background gauge field. And now gauging means sum over all of them, if you want average. So you can sum over all those guys. What is the sum over? Well, this is exactly the same discussion that we had last time on Maxwell. In Maxwell, we wrote the action, and then you remember we wrote the action was the usual thing, 1 over 2 e squared, A1, VA1, star VA1, okay, that's the Maxwell action. And then I wrote the partition function, and I said we have to integrate over all A1 of e to the minus s, and then sum over what? And we had this whole little discussion intermezzo with the check assignments, characters, and so on. That's the thing you have to sum over. So that's the same thing here. You have to sum over those. I write it as a sum like this because we will mostly deal with finite or discrete symmetries, but in principle, you have to sum over all those sets. So you have to sum over, so this B, T plus 1, are in, let me write symbolically, in this check assignments, T plus 2, but it's not too important. We sum those things. The result is a new partition function. This is the partition function of the gauge theory. So if this was T, this is T gauge by G. And maybe there is a coefficient influence. I leave unconstrained for the moment. So that's what it means. You see in particular that whatever, when you have the symmetry, let's think of you want symmetry, it means there is another current and so on, and that's what you use to couple. So you have used, in this, you have used the fact that you can, in the action, you can add a term that couples the nutter current with the B, and then you sum over all the B's. So the nutter current is no longer there to be coupled with anyone, it's summed over. So that guy no longer has this symmetry.
But do you act like a kinetic term for this field, or?
Yeah, very good. That's excellent. So indeed, there is an ambiguity in the way I gauge. The ambiguity is, there are two ambiguities. There is one that I already mentioned last time, which is couple this set here is not it is well defined, but there is no unique way to do this. You could add indeed a kinetic term. For instance, you could add this B. You remember I discussed the fact that you could add anything that depends on dB. In particular, if you want, you can add integral of dB wedge star dB, which is exactly the coupling. So if you do that, so for instance, okay, a very trivial way to obtain Maxwell theory is to say, I take the trivial theory, no field, no action, S equals 0. It has a U1 symmetry, which acts on nothing, but okay, I can still pretend it's there. And then I introduce the background field for that. It couples to the nutter current, which is 0, so it couples to nothing. But then I can add a kinetic term, so I can add this to the background gauge field, and then I sum over, and I get Maxwell. So one way to get Maxwell theory is to start from the empty theory and gauge the non-acting U1. So that's the first ambiguity. But of course, it has massive impact. So that's one thing. And then there's another thing, which is here I could, if I wanted to, I could add maybe some coefficients. which depends on BP. See here, I put all these coefficients equal to 1, but maybe it would be consistent to add some coefficients here. And yeah, we will see this play a role in it. Okay, now I will be very brief about gauging because I just want to say a few more things. So let me just write it because it's important. So, first of all, there is the coupling to background gauge field involves some choice. For instance, adding kinetic term for the background gauge field. Second, we could add coefficients in the sum. Third point, well, actually, again, let me just mention one thing briefly here, that these coefficients can make gauging look like a Fourier transform. That makes sense. So I will have one more remark here, but let me explain what I mean by this exactly. Maybe you can get it. Here you have this sum, but now by combining these remarks that I put here, I could define another way of gauging. I could say, oh, actually, my gauge theory I put some coefficient and then I put the sum over the b plus 1 of z of b. And then the coefficient I put has a very specific form, exponential of coefficient yi is that integral over space-time of b wedge b tilde. We put the indices, so b is a p plus 1. So then this b tilde has to be, we have to sum up to d, so it's d minus p minus 1. Right, so I could add, this is what I mean by a coefficient. But now you see this coefficient depends on another field. Depends on b tilde. This b tilde is now an argument here. B minus p minus 1. And now this should really be reminiscent of Fourier transform. And in particular, you could identify that here we have been able to couple the gauge theory to a background gauge field. The difference is the degree has changed quite a bit. So when I said that the gauge theory no longer has the symmetry GP, it has no longer GP, but it might have another thing with degree what? It has symmetry G twiddle. And the degree is 1 less than this, so d minus p minus 2. And now I could gauge that one. So now I take this, I gauge, so I sum over the b twiddle, and I can of course add coefficients. I can call them b again. I put the exponential, maybe with a minus sign, and so I do the Fourier transform in the other direction. So this guy would be gauging G twiddle. So you see that gauging is actually not the thing that you might naively think that it's something that destroys some information, like an irreversible process. Actually, it is reversible at least in some cases. Right. We have a theory to gauge and then something new appears. So sometimes that guy here is called the quantum symmetry. So there are this was observed very, very long ago in like in 2 dimensions. So you see, if you take d equal to 2 and p equal to 0, that G0 gives back G0. So in 2-dimensional theories, if you gauge, then there is actually a new usual symmetry that reappears. That one was called the quantum symmetry in maybe 40 years ago. And then if you gauge the quantum symmetry, you're back to that one. You can keep doing. Okay, so that was my remark here with Fourier transforms. I'm not too, yeah, don't take this too seriously. But let's say if the symmetry is Dn, for instance, this will work. Z, then maybe the dual would be U1, and this kind of thing. If it's something crazy, maybe there will be subtleties. Maybe you cannot couple this way if G is not abelian. So it's we put some quotation. I just write this as some intuition. That was just a comment. And then a last comment, super important one. There is always this comment about non-anomalous. Why is it there? Well, as you know, the anomaly will be if Z B plus 1 is not equal to Z B plus 1 plus gauge transformation. And you should just consider that's an important point because it allows you to understand why an anomalous symmetry is still a perfectly good symmetry. Because if you have a symmetry which is anomalous, it's fine. You have the partition function and then you change it and you have the same, it's to a phase. It's just a number. That's not really a problem. A global phase, never hurts anyone. Here, you sum over all those things. So here it will depend on these phases. You have different phases summed over. These things will interfere. And the interference between all these phases will depend on the choices you make. So this means that if there is an anomaly, definitely gauging will be ill-defined, impossible. So an anomaly, fine as long as you don't gauge. If you try to gauge, very bad. Okay. And then I skip what I wanted to say more on gauging. Any question?
Maybe this is a bit naive, but yeah, I find it interesting this way of adding this exponential. It's, naively one would just sum over these additional fields.
Yes.
So can I think of this in a way as just, as modifying the action and then summing over a partition function in the usual way, or is it really something new?
Yeah, if you want, you can say that you modify the action by adding this term and by also introducing this extra coupling maybe, and then you sum, and then the coupling. Again, if you're in 2 dimensions, that's just a coupling, and then you recover another thing that depends on this coupling. So it is a modification of the action, but really seeing it this way, I will show some examples now with the Young-Mills just in a minute, but it shows that there are, the fact that a new symmetry emerges is one thing, and then how it emerges depends really on the coefficient that you put. So here, for instance, I put 5, I could add some integer, but if I put k, now I have as many ways of gauging as the integers k. And each one will give me maybe something different, or maybe the same, but we will see some examples now. It's just the fact that I want to emphasize that gauging first destroys the symmetry, but a new one emerges. And it's not, you cannot just say, oh, let's gauge the symmetry. You have to be much more precise and explain how to do it. Okay. Great. So now we move to the third part on Young-Mills. So we want to use this formalism in order to not learn, but at least describe some things, some things about good old Yang-Mills theory and variations with matter and so on. So QCD, standard model, they are relatively important theories. So what is Yang-Mills? For those who don't remember, we start from G. So now confusingly, G, for the first time in this lecture, will not stand for a symmetry group. G will be the gauge group, G for H. If you want, you can do as I just explained before. You can start from the empty theory, pick some gauge group, one SUN, and say that it acts trivially, couple it, gauge it, then you get Yang-Mills, provided you add the proper couple. But okay, I will not do it in this kind of stupid way. Let's do it in the normal way. So G is the gauge group. I do not have G. I don't know how to do fractal, but that's supposed to be fractal. That's the Lie algebra of G. And then our basic field is an A. So as per my conventions, I denote it with lowercase because it's a dynamical field. It's the same as in Maxwell, except now it's a Lie algebra valued. Okay, let's add now some restriction. Gauge group, I take it to be compact, simple. D group, think of SUN if you want. And this is now Lie algebra valued. In particular, it's non-abelian in general. Otherwise, we don't call it Yang-Mills. It's non-abelian. A is the Lie algebra valued field, and now F2. In Maxwell, this was just dA. But now, because of the non-abelian character of G, we have to add some correction, which in my convention, this would be minus A. It doesn't really matter. Let's okay. And then the action of Yang-Mills is there is the coupling constant, G Yang-Mills over here, integrate over all of space-time. I will be in 4 dimensions. In my notation, capital D is 4. So we sum over MD, which is 4-dimensional, and then we take just the trace of F2 where star F. And well, I don't want to extend too much on this, but all the caveats of my discussion of Maxwell apply here, of course, and much more. So in principle, in particular, yeah, this F2, well, now it's clear that the F, you see, is not an exact form. Maxwell was a bit. Okay, so that's the action. Now the question is, what are the symmetries? That's question number 1. Question number 2. It seems that the gauge group plays no role. What is the role? What role is played by G as opposed to the Lie algebra? It seems that everything depends only on the Lie algebra because the actual value gauge group does not appear. Question, and what did I? And there's also the possibility to add what's called the theta term, something like theta over I squared integral of trace of F2 wedge F2. The difference is the star, yeah, there's no star. But that term is a topological term, and because of that, it will naively not contribute to computations of scattering of particles and so on. But what does this do? I'll try to answer all these questions using the framework of these symmetries. So,
Third one is not a question.
yeah, but okay, which okay. What is the effect of this? So now we have our recipe that computes symmetries for us. So in principle, question number 1, we'll all be able now to answer it because I have number 4, which allows me for any p to know what is the p-form symmetry. Use it to answer the first question. So we know that GP is just the set of p-dimensional operators in mod screening dual of this. Okay, so we have to look for the p-dimensional operators. As in Maxwell, there's not so much we can do. We have only F at our disposal, or maybe A. So A is actually the fundamental field. So we can try to mimic what we did with Maxwell. And there were these very nice Wilson lines and Tooth lines. So let's try to do the same. So we quickly ran into a problem because this is Lie algebra valued. So in Maxwell, we had this exponential of I times the integral over some path, gamma 1, of A1. Well, now this thing, you can think of it as a bunch of matrices that depend on the path. This exponential is not really well defined, but it's a standard trick. I guess everyone has seen this, that there is the path ordered exponential. So I add this p, that's what it means. It's just a technical tool that allows me to actually compute this when the group is non-abelian. Okay, so that's fine. Yeah. There's one thing I didn't say, but I guess everyone knows that A, that whole thing, like Yang-Mills, is a gauge theory. So there is a gauge redundancy in this whole business. Maybe I should just write it. In Maxwell case, it was just A1 is equivalent to A1 plus D of something. Now it's a bit more involved because of the non-abelian nature of the group. And now you should rather write, so instead of having just a small lambda, which is valued in the Lie algebra, I have a capital lambda, lambda A lambda dagger plus have a plus I here, lambda D lambda. That's the gauge invariance. This is the adjoint action, act by conjugation. If the group is abelian, then you see that one goes away. And then from here, if you think that lambda is e to the I little lambda, that thing here will give you back the d lambda that we have in Maxwell. That's the generalization. Okay, so that's how gauge invariance is works. And so now on this thing, if gamma is a path that goes from x to y, and if I implement a gauge transformation here, then you can check that this actually transforms with these factors lambda. So basically, with this I define as W of gamma 1. I define W as this. Then under a gauge transformation, W of gamma goes to lambda of x, W gamma lambda of y. Not gauge invariant. And even if you take the trace, still not good because these are different points. Lambda is the function of space-time. But if you take a loop and you take the trace, then all of these things go away and that's the Wilson loop. So the Wilson loop, so I don't take exactly this definition, I modify it a little bit. So I take a trace in addition to that. Trace of all of this, where gamma 1 is a loop, which has no end. And what else should I say? Yeah, I should say that this is still not really a well-defined expression, because A is Lie algebra valued, but in principle, I could take A in any representation I want. And when I take a trace, I need to say the trace is the trace of a matrix. So I need to represent my Lie algebra as a bunch of matrices, and that's the representation. So I can put an index R here. So R is in which representation A sits, and R will be then a label here. Okay. Put this in a box, important one. So that is the Wilson loop. The most naive generalization of what we had in Maxwell. That one is gauge invariance because of the. Of course, it's not topological. Compute it if you change the path gamma, it will depend in a very complicated way. It's not topological. I say this because if it was topological, then we could use this in our definition. There we go. We would have a symmetry. Fortunately, okay, but still, maybe it can play the role of a charge. This is what the case in the Maxwell field. That. So, question. We have to use this equation. So, can it be screened?
That's not right, but
I said that if you define the Wilson line with ending points, yeah, that was the expression I had before in the trace wasn't well defined. But now, can this one be screened? So, is there a way to have a Wilson line? A loop, the loop, but can I open it? So can I put some operator, which indeed would be non-trivial? If it's trivial, then we saw it's not the case. But can I do this? Are there operators? In Maxwell, there was none. What's the difference? The answer is yes, it can be screened, but what can I put here that I did not have in Maxwell, but I had here? Yeah, exactly. The gluons are charged. That's the difference. So in Maxwell, photon is not charged, but the gluons are charged. So in other words, what I can put here is, so not for any representation, but if R is the adjoint representation, here I can put W adjoint, and now here I can put an insertion of the field strength F. So F is not gauge invariant. It transforms how, well, I didn't write it here. F2 is equivalent to lambda F2 lambda. It transforms in the adjoint representation. So now if I put the adjoint representation here, then that is well-defined gauge invariant. So because of the gluons, W adjoint is spring to nothing. Means here I do the identity. So okay, so already the symmetry will not be all of U1 because we have killed a whole bunch of. We have not killed only the adjoint because we have to take the quotient here. So what is remaining? So let me make a little illustration. Let's say the theory is we look at SU2 Young Mills. If it's SU2 Young Mills, then what is the set of representations of SU2? Well, I can represent them on an axis. It's the spin, 0, there's 1/2, 1, 3/2, 2, and so on. These are all the representations. which one is the adjoint? The adjoint representation of SU2 is spin 1, like 3-dimensional. So that guy is screened. But now I kind of assume that this is a group, right? So it means that every integer spin is actually all the integer spins are screened. So what are all the lines modulo screening? And I have a two-group element, just those two. There's a Z2. And then that thing is Z2. Then I take the dual of Z2, it's still Z2. So the one from symmetry, the one from the symmetry contains at least a Z2, one from symmetry. Okay. Here's the representation. Let's do one more example, slightly less true than SU2, SU3. I'm kind of assuming here that representation theory is known. Otherwise, if you don't know, then you can forget the next 5 minutes and we can begin later. If you do SU3, then the representations are given by the weight in the fundamental Weyl chamber. We have the origin 0, that's the trigger representation. Then here you have the fundamental. Let me denote it as a box, fundamental. Here you have the anti-fundamental. That's the fundamental. That's the anti-fundamental. Here you have another one. What is this one? The adjoint. Then you have second rank symmetric, second rank anti-symmetric, and so on. Right? These are all the representations. So for each of these points, there is a Wilson line, Wilson loop. And this one is strict because that's the adjoint. Now you can see that anything which is in the product of itself will also be screened, and that generates a lattice. Contains this point, this point, this point, this point, and so on. So what is not screened is whatever is below, in the cell below. So this is not screened. And you can see that the structure here is a Z3 actually, generated by this guy. If you take twice this guy, it arrives here, but then modulo the adjoint, you come back here. So in SU3, there is a Z3 one from symmetry that you obtain from this picture. And okay, now I guess you understand the logic, do SU4 and so on. The result is the symmetry of SUN means is Vn. And that's it. So it's very strong. Things I have not shown. So I hope I have convinced you that with the Wilson loops, you can already generate a Zn one form symmetry. And the claim is there is nothing else. That's what this thing is. So in particular, you could complain, but what about the magnetic ones? But the point is, magnetic ones are not there. If you try to do the analog of this with soft lines, you will not manage, because to construct soft lines, you have to, you have to find monopoles for SUN and insert them along a line, And monopoles, in order to construct them, it's as U1, you have an S2, have an S2 like this, yes, have an S2, and then you have to use the fact that on the two patches of the S2 you have a circle, and you use the fact that the pi1 of U1, the first fundamental group, sorry, the fundamental group, the first homotopy group for U1 is V, and that is the monopole number. But in Yang-Mills, pi1 of SUN is trivial. There's no pi1. So you cannot construct monopoles, so you cannot construct two flanks. And then, why is there nothing else? Well, you can, by exhaustion, you never find anything, so then that's it. Any question on all this derivation? I was quite fast at the end, but
That with one form symmetry.
Yeah.
Layer forms.
yeah. So the claim is there is nothing.
Have some non-trivial. Like,
Yes, that's true. Actually, yeah. Yeah, but we are in 4 dimensions.
The local operator.
For the Yang-Mills with SUN. But yeah, I have not proven all of it. But indeed, you should check you should check in particular the pi2 that you cannot do something with two-form symmetry. Okay, so now from there, we have answered our first question. I erased now, but what was the symmetry? Second question was, what is the role of the gauge group? It seems it doesn't play a role. I've used the representation theory of Lie algebra. That's the Lie algebra SUN. But still, there is something that I have hidden a bit. The fact that in here, these are representations of G, of the gauge group. So in particular, if the group was not SUN, but something else with the same Lie algebra. So for instance, let's say SO3, which is SU2, has the same Lie algebra, but it's different group. If I make the same drawing as that, what are the representations of SO3? 0, that's the integer space. Now I look for screening. This is screened, everything is screened. So there's nothing. So no one from symmetry here for SO3. Except that now this thing has to be revisited. Pi1 of SO3 is now actually Z2. Right? That's the standard thing, with the belt and so on. So here it is possible to have magnetic monopoles. Actually, there is so you can construct one non-trivial 't Hooft line. So there will be a magnetic symmetry, which is Z2. So that allows to construct 't Hooft line. And then there will be a Z2 one-form symmetry, except it's a magnetic one. So let me summarize this. And then I give some general result, and then I think the phases will be for next time. But at this, I answer my second question. I will also try to answer the third, the theta term thing. So let's compare the two theories. So I had SU2 theory, and then I had SO3. In SU2 theory, it's this drawing here. I have one non-trivial Wilson. This guy. This guy is a non-trivial Wilson. That one cannot be screened. It's there, and its charge can be measured. So it has Wilson. that guy here has a non-trivial two-flat. So the symmetry, these are the charge operators. So the symmetry in both cases is Z2, one form symmetry. And now actually there is a relation between these two. And you guess what is the relation? How can I connect these two? Yeah, gauge. You cannot read it, but I here gauge. What do I gauge? The only symmetry I have, Z2. And you see we have SU2 theory. You gauge Z2, you're back with Z2. It's not the same. This one was electric, this one is magnetic. So this is an example of this Fourier transform thing. Like you're here, gauge it, you go back here. You cannot get rid of the Z2. You can just push it in a different domain.
Are two theories related that way? Are they isomorphic in some way or not?
No, not at all. Not in general. Sometimes yes. So actually, yeah, sometimes yes. So for instance, we will discuss this in the last lecture because that's where some of the non-invertible symmetries arise. That secretly an SU2 and an SO3 theory are the same. The easiest way to do that is to put maximal supersymmetry. If you put n equal 4 super mills of this and this, actually there is S duality that says that this is the same as this, provided you invert the. Now, if you are at the self-dual point, G Young mills equals 4 pi or something like that, 1 over 4 pi, then yes, they are the same. But then there is a case where gauging gives you an isomorphic field. That's a very exceptional case, which leads to these non-invertible symmetries that we will discuss. Okay, so I'm almost done with that, but not completely. So yeah, I guess this answers the fact that the gauge group does play a role. But I'm not completely done. Let me be a bit more explicit about the line, the charge operator. And let me put them on a drawing. So here I put the electric charge, and here I put the magnetic charge. All the theories always have the identity, which is not charge. So this is the point here at the origin. And this guy has a Wilson line, which has electric charge here, 1/2, and no magnetic charge. So it sits here. And then because the group is Z2, and that's I erased that, but that was modulo screening. Now, if you undo this modulo screening, you have charges on the lattice generated by this. And there was also the fully screened Tuft line, which is here at 2. So you have something like that. You can continue the lattice. That's the fundamental set. The same drawing here is like that. So these are all the line operators. And now there is one more question, which was the role of the theta term. And actually there is I don't really have time to say all of it, but the periodicity of the theta term, so I wrote the theta term was this term, theta over 16 pi squared integral of the trace of f with f. There is no hot star here, so it's a topological term. It does not depend. But it has an effect on the global structure of the theory. And in particular, the periodicity of theta is related to the fundamental root. And in SU2, this will be 2 pi periodic. So if you shift theta by 2 pi, you don't change it. But in SO3, it's 4 pi periodic. So what happens if you shift theta by 2 pi in an SO3 gauge theory? Well, you're still in SO3 gauge theory, except that now theta is equal to 2 pi, not to 0. But 2 pi is not equal to 0 because the periodicity is 4 pi. And so what you get is another theory. And then there is something called the Witten effect, which is if you shift theta by an amount, then the magnetically charged object, or magnetic monopoles, or any magnetically charged thing, acquires an electric charge. And in SO3, indeed, we have this guy, which is magnetically charged. And it will acquire an electric charge, which is equal to its magnetic, to become a dynamic line. It's neither Toft nor Wilson, is kind of a mix between the two. And so the same diagram here would be this. Still an SO3 theory. Except they are not the same theories. They don't have the same lines. The difference is the theta angle. So that answers my third question. And in order to distinguish them, the theta angle, because the periodicity is just twice the normal one, there's just a twofold ambiguity to, so we put a plus or minus. So maybe we should put 0 or 1. If you remember, when someone asked the question about gauging, really almost about gauging, there was this possibility of adding such a coefficient, and I said, oh, but you could put some k in front, whatever integer. Then you gauge with that. Here, this gauging, I implicitly assume that it's the gauging with 0. So now if you gauge with 1k, it amounts to adding a theta. So actually, this index refers how you gauge. So you can gauge differently and arrive here. So the symmetry is still Z2, of course. And this is a dynamic line. Okay, so there are actually 3 theories which have Lie algebra SU2, 3 Young-Mills theories, depending on whether or not you activate the theta term. This has theta term, this does not have, and the spectrum of line operators is good. I think I should stop here. So next time I will do the phases, but I should just write the final results. Now this was the example in SUN. Let me just write the final result for Young-Mills. Usual generalization of that, but for any group. Young-Mills, pure Young-Mills with gauge group G and 0 theta term has an electric one-form symmetry, which is center G, and a magnetic one-form symmetry, which is the dual of the fundamental group of G. That's just, I need to at least have written this. So for SUN, we said that this is trivial, and the center of SUN is just the end, so that gives back this. If you take SO3, SO3 has no center, but it has a high one. We still get the Z2, and I'm at theta equals 0, so that's all I can say. And then in general, when you do gauging and so on, you might get the same group as here, but sometimes you can get something else. So I will say more next time. So yeah, I stop here. If you have questions, feel free to.
So questions?
Also, you seem to have a general formalism based on extended objects, but at some point you're using the path integral. Okay. Yes. For example, for gauging, you remove path integrals and do everything more abstract.
Maybe. Well, I can't now. Maybe there is a way. I'm not sure what you have in mind for more abstractly. The path integral format can already be made quite abstract. As a, if you just say it's not an integral, you can say it's the functor from the category of Bordisms into the right target category, and then you ask for various axioms to work, and then this ties in with the. I will explore a bit this direction next time. to talk about anomalies and so on.
But if I have a theory which has no Lagrangian network, so can I gauge it?
Yeah, sure. So the only thing you need is the pattern table. So indeed, the partition function. Yes, not the pattern table. So partition function. Actually, next time I will need to introduce some topological field theories, for which you don't need to have a path integral and a Lagrange. Sometimes you can have it. So actually, this is one of the things I skipped when I said that the gauging. I wanted to talk a bit about pure ZN gauge theory with nothing else. This can be written with a Lagrangian and an action as a DF theory, but you don't need to. You can also write it more abstractly as a thing that computes you the this on manifolds. So yes, you can definitely do without an action. Now, in practice, it depends what you want. More questions?
Or maybe I missed, but when you were referring to adding
There is a question online. Maybe do it after.
Already online. Please online talk.
Oh, thank you very much. I'm sorry, can you hear me already?
Yes. I can hear you, yes.
Okay. I just want to ask, are there instructions minor form symmetries without the next
Actually, we don't hear.
Could you write down the question on the chat if it's possible? Sure. Sorry.
I'm going to mention P. P equals -1. Okay. Yes, maybe. So indeed, so -1 form symmetries exist, and you can make sense of them. Actually, you can even go to lower, -2, -3, as much as you want. So what does it mean? Okay, there is a kind of a trivial way of making this work. You can always say, okay, that's one of the things I wanted to say actually at the end of this, how if you have say, one form symmetry in a d-dimensional theory, and then you compactify to one lower, for instance, you put it on a circle, that will be very useful when we want to study the confining to Higgs transition in Young-Mills. We put the theory on not on R4, but on R3 times a circle, 1 and R3. And then what does the one form symmetry, let's say this one, what does it become? Well, the Wilson lines, you can either have them here or wrapping the circle. If they wrap the circle from the point of view of 3D, they become one form symmetries, 0 form symmetries. While from here, they become one form symmetry charges. So from 1, we have gone down to 0 and 1. And you could still do this. So you can always say that you have a p-form symmetry, and then on a codimension whatever, you get p minus that number symmetry. And indeed, the coupling constants, so like the theta terms, can be seen as -1 form symmetry defect operators, because then that would be codimension -1 plus 1, which is 0, which means fully covering all the space. Yeah, so that the question was, are you going to mention them? Yes. Yeah, in quantum mechanics. Yes, exactly. So I will, next time I talk about anomaly and so on, so I will do exactly what you say. Yeah.
Can you read it? Because
yeah, so he's asking because in simple quantum mechanics, in 0 plus 1 space-time dimensions, there is not much space for extended operators, but and indeed there will not be much extended, but I will talk about the theta angle in quantum mechanics in relation with anomalies. Yeah, I will talk about this. Then there was another.
I missed, but you were saying that the gluons are charged, so you can attach them to the muscle line. But and you denote this with addition of F.
Yes.
But the F transforms as well. I didn't
Yes.
get how does it make it?
Yes. Good. So when you have it's slightly confusing because it's the adjoint. So let me do it in general representation, and then at the end we say it was the adjoint. So if you have a Wilson line that doesn't, let's say that ends only here, but here goes to infinity, then I wrote at some point the transformation was the Wilson line goes to Wilson line times lambda dagger at y. So here, if I add a field that transforms, let's say I add a field f of y, which transforms under a gauge transformation as lambda f under y f of y, then the concatenation is gauge invariant. Now, in particular, if we take the adjoint, I can write it in a matrix way in such a way that it's done. Of course, in the standard way, we write it by sandwiching, and then it looks like we have not done anything, but actually you should really write it in the adjoint and acting from one side, and then that works. So that's how.
So you also mentioned that you can put an interface between two different theories.
Yes.
I mean,
Yeah.
So whether that is really, it's like two same series.
Yeah. It's just not a symmetry. It's just an interface. It's just that we can naturally extend this to having you can extend the formalism with no cost except that you replace the having one object by no constraint, and then you just describe different theories. If you want, you can see them actually in the. To see. You can write my drawing, and this will also connect with what Mathieu was asking. In my drawing, I had points. Point was my theory, and then I think I had the red arrow, which were the symmetries, and then and so on. Now, if you say actually I don't have just a theory, but I have interfaces, and I have 2 points, and then I can now have arrows like this. So this would be my interface between 2 different theories. But now let's take seriously this idea that everything is just arrows piled up. So this would be a 0-dimensional arrow. So let me draw it with a dot, which acts on something else. So now, what is that? I have 2 dotted things acting on the something else. Now we are back in the same framework as before. We have one object. The object is of codimension -1. What is it? It's the coupling constant that Mathieu was asking. Because when you go, like what this arrow means is a kind of a set of coupling constants. And then you go from here to here. Like let's say you have a big parameter space of all the Lagrangians you can write. That's one Lagrangian. That's another one. It has some coupling constant. It has some other coupling constants, and then you have an interface between 2 theories. So theories are kind of these 0-dimensional arrows.
But why to be a symmetry? You want the interface to be topological.
Yes. Yes.
So that's a huge constraint.
Yeah, that's a huge constraint. Also, it's clear in which space does this thing vary. So we should extend space with varying coupling constant maybe. So yes, but that's why I didn't really mention it. But I don't know exactly. I don't know how fully precise this picture is, but at least for the discussion at the end of the lecture, I think it's fine. Then you could ask and you keep going. Maybe we talk about this next time, in the last lecture. Any other question?
No. So thank you, Antoine. So next lecture will be next Friday at this Friday at 10 o'clock. So.